So in today's world, every deep learning model from ChatGPT to Tesla's self-driving cars runs on a single yet powerful idea: the gradient. Without gradients, a neural network is just random numbers, blind at guessing and static. But with gradient, it learns, it evolves, improves, and gets smarter with every iterations. So what are gradients and why are they so important in deep learning? Let's decode this step by step. So, this whole idea of gradient isn't new. It was born centuries ago with calculus, which is invented by Newton and Leibniz. They wanted a way to describe how things change over the time, how fast an apple falls, or how fast a planet moves, or how a curve bends. This idea of change, of slope, became the derivative. Now, let's fast forward to modern AI. We still use the same math but now for learning. Now, in context to deep learning, the gradient tells our network or model how much our model's output changes when we tweak certain parameter. And that is everything because learning is just adjusting its parameter to reduce error step by step. Now, let's break down this concept of gradient and what this really is. So imagine a simple function of f(x, y) equals to x square plus y square. If we plot this, it looks like a perfect 3D bowl. The lowest point, which is the minimum, is at the right bottom where both x and y are 0. Now what happens if we drop a marble ball somewhere on the surface? It will naturally roll down toward the bottom. The direction it rolls in is not random. It depends on the slope of the surface at that point. Now that slope is what we actually call the gradient. Now mathematically, if we look at gradient, then gradient is a vector that points toward the direction where the function increases the fastest. Now in our case, let's have a look at our example of x, y equals to x squared plus y squared. If we take a partial differentiation of or derivative of this function using the formula, then we get 2x and 2y as the gradient. This means when x and y are positive, the gradient points outward, which is uphill. When they are negative, it points in the opposite direction, still uphill for that region. In short, gradient always points to where the function is increasing the most, irrespective of the direction. But in context to deep learning, our goal isn't to go uphill, it's to go downhill to find the lowest possible value. That's why we move in the opposite direction of the gradient itself, and hence we call this negative gradient. And this simple idea is the foundation of gradient descent algorithm. Why gradient descent? Because we are trying to find the lowest possible gradient, hence gradient descent. Now to understand this even more clearly, let's do a small step-by-step example with one variable, which is easier to visualize. So let's say I have this function f of x, which is equals to x squared, and we want to find the value of x that makes this function minimum. So our step 1 should be to choose a starting point. Now, in deep learning model starts with the random variable or random parameter. Let's do the similar thing and start with absolutely random variable. Let's say I want to start with x. So in this case, my x will be equals to 3. Now, let's compute the derivative. So f dash x equals to, with the formula n x raised to n minus 1, we get 2x. And if we put x as 3, we get 6. Now in this case, the gradient is positive, meaning the function increases as x increases. So to minimize, we have to go in opposite direction. So step 2 will be towards that. Take a small step opposite to the gradient. So for that, we have to update our x using x. I'm going to call this variable x new, x minus alpha times f dash x. Now let's talk about this alpha. This alpha is the variable that decides by how much we want to go back in opposite direction. In some textbooks, you'll see this variable as eta, and in context to deep learning, this is something called learning rate. And this variable or this learning rate decides by how much I want to go in opposite direction. So let's say in our case, I want to set my alpha to 0.1. This is something that you decide for your model. So when we put alpha as 0.1, we get 3 minus 0.1 times 6, which is equal to 2.4. So now you can see we are already minimizing our loss or minimizing our gradient in this case. Let's repeat again. So let's move to step 3, which is f dash 2.4 equals to 2 times 2.4, which is 4.8. So what we did here, we simply put our updated x new to this function and we get 4.8. So our gradient is already minimizing. Now let's find the updated x new. So x new equals to minus 0.1 times 4.8. And now we get 1.92. Now if we plot this new x value to our derivative or gradient, we get 3.84 after calculation. Similarly, the updated x new value that we'll get is 1.536 and so on. So you can see the pattern here. The steps get smaller as we approach to 0, which is the minimum. Now this learning rate, alpha or eta, comes with its own pros and cons. What I mean by its own pros and cons is because you can ask questions like, what if we set learning rate too low to find the optimal minimum? So let's say imagine we pick alpha as 0.001. Now that means even though we know the right direction, we are only taking tiny baby steps downhill, which is good. We won't overshoot. Our network will be stable, but it will take forever to reach the bottom. The model will run very slowly, taking thousands of epochs to reduce the loss even slightly. And you'll probably end up paying too much for your resources. And by resources, I mean GPU power and GPU computation. And on the other hand, if we increase our learning rate too much, let's say we set alpha equals to 1, in that case, our steps become too aggressive. We might jump past the minimum, bounce to the other side, and overshoot again and again. And the loss might start oscillating, even increasing, and the model can completely fail to converge. It's like driving downhill at full speed, and you'll probably end up skipping the global minima. So the correct way is to choose the optimal learning rate, which is big enough to make progress, but small enough to stay stable. This is where gradient descent shines. The model learns efficiently, reducing the loss quickly and smoothly converging to the minimum. Now, when you train a neural network, you start with random weights, as we just saw with our dry run. You feed data forward, the model makes prediction, then you compute loss, how wrong the model was, and in which direction we should adjust it to reduce the loss next time. Now comes the magic, the gradient of that loss with respect to its weight, and this tells us how much each weight contribute to the error. Now this is the essence of learning. The model uses gradients to see the terrain of its own performance. Without them, it's like walking in the dark. But with them, it follows a precise mathematical compass toward improvement. So in Pytorch, every time you see dot backward, it's gradients at work, flowing backward through the network, updating each parameter just enough to get bit better. And gradient makes deep learning more robust because they allow continuous fine-grained learning. So instead of random guessing, your model takes informed steps. Even with millions of parameters, the gradient efficiently guides every weight in the right direction. That's why network can learn from complex data. They rely on this tiny slope information to climb toward intelligence. The better our gradients, the faster and more stable our learning process is. Now you know what gradient is. It's the mathematical core concept of deep learning. But here's the question. How does Pytorch actually computes these gradients even for thousands or millions of operations so efficiently? That's where AutoGrad comes in. So in the next video, we'll open this black box and see how Pytorch automates the differentiation for every tensor in your network. See you there, and thank you so much for watching.